Hey guys, I'm going to do a short little intro on torque, kind of playing off of the assignment I gave you in quizzes to kind of introduce the idea of torque. Okay, torque we said was kind of like a rotational force, so it's a rotational push or pull. So the equation for torque is this. So you have the Greek symbol tau, kind of a funny looking T, is equal to a force applied at some distance away from an axis. Okay, so this distance refers to, we call that lever arm, right? Okay, so that's lever arm, and that's in the units meters, so that refers to like the distance that a force is applied away from an axis. And this is obviously the force that's applied, that's in newtons. Torque has the unit newton meter, so unit for force, newtons, times the unit for distance, which is meters. So say you take something simple like a door. So here's like looking at a door from above. The little circly part is the hinge. Let me get a different color here. So here is your hinge, and here's the door. We're looking at it from above. And if we apply a force here versus here versus here, okay, and all three of those are the same force, this would be the largest torque, this would be a smaller torque, and this would be a very small torque. Okay, applying a force out here gives you leverage. Okay, that's kind of where the word leverage comes from. Okay, it'd be a lot easier to open the door from here. So in order to make rotation easy, okay, in order to rotate something, you need to apply a torque. To apply lots of torque, you want a lot of force far away from the axis. Okay, so the lever arm, okay, so for this first force is only about that much. That's not very far. The lever arm for the second force is this much. And the lever arm for this third one is this much. So here we have this big lever arm which creates a lot of torque, which means that to rotate it at a certain rate we don't need as much force, which is what makes it easier, right? Okay, so anytime a force is applied some distance away from an axis, you are not going to be able to rotate something. So say here's another rotating object. Say here's the hinge of a door, and here's the door. Didn't draw that very good. Try that again. So here's the door. You know, if you applied a force to the edge, so say you applied a force like that to the door, that's not going to cause any rotation. Nor is a force applied here. Okay, so we have no torque here and no torque here. This force, because there is no lever arm, it's right on the hinge, that can't apply a torque. Okay, you need some kind of lever arm. This force is not going to apply that. It is applied some distance away from the axis, but because it's not perpendicular to the rotating object, okay, it's right towards the hinge. Okay, if it's directly towards the hinge, there is no perpendicular component of this force that's going to cause a rotation. However, if we applied a force at some angle like this, you have a torque. Or some other weird angle like this, you're going to again have a torque. So get rid of these guys that don't cause a torque. Okay, so this force has to be applied perpendicularly to the rotating object, or kind of, you'd say, perpendicular to a radius of the out from the axis, I guess would be a more proper way of saying it. Okay, so maybe think of, instead of a ball, and say we have a ball here. Sorry, it's kind of hard to draw a great circle. Try this one with my hand. It's a little bit better. Okay, now if you applied a force here, so let's imagine this is like a basketball or something. If you applied a force right through the object's center, that's not going to really cause any rotation. Or even like this, so that's not going to cause any torque. But if I create instead some force that is applied here, okay, that's perpendicular to the surface. That's going to drag this surface. It's going to cause this surface to rotate around its axis. Okay, a ball, its axis would kind of be at its center, right? Okay, and anything kind of that is perpendicular to a radius. So here's a bunch of radiuses out from the center of this ball. If you have a force that is perpendicular to any radius of the ball, that's going to create some torque. But if you make a force that is just parallel to that, no torque. Or radially outward, no torque. Okay, think of, like, if you know anything about baseball, the only pitch in baseball that you pitch with that doesn't have rotation is a knuckleball. And because it doesn't have any rotation, it acts kind of weird. But in order to create a knuckleball, you have to push it. You almost like push it through its center. Any other way you throw a baseball, you are kind of applying a force to its outer edge and causing it to rotate. Usually, if you want to throw a curveball, a slider, something like that, you want a lot of force to its outer edge. Okay, so there's some of the basics. I'm going to try and keep this pretty short here. So, gravity can also create a torque. Okay, we're going to do a short little concept builder here where you can practice some of this. And like 90% of it is super easy. All of it's pretty easy, but a lot of it's like crazy easy. So, imagine we have a balancing object. Okay, so here's like a pivot, or what you might call a fulcrum, and say you have a meter stick. Okay, now this fulcrum here is right at the center of this meter stick, right at the 50 centimeter mark. Now if I just put some rock over here, that's going to cause the system to rotate, right? Because its weight pulls it downward, and that weight is acting some distance away from the axis. So say this was at like the 80 centimeter mark, or something like that, and the axis is at 50, okay? You have this weight, and it's acting some distance away from the axis. So that's going to create torque. However, if I put an equal-sized rock on the other side, and it's the same distance away from the center, you know, it may not look like it, but say these two distances are the same, that would create no rotation, because equal torques on either side of that. This would try and be rotating it counterclockwise. This one over here on the right side would be trying to rotate it clockwise. You'd have two equal torques, and two equal torques means two equal and opposite torques. This is a counterclockwise torque, and the one on the right side is a clockwise torque. You have equal and opposite torques. You wind up, you know, like anything else that's equal and opposite, they wind up canceling each other out. So when you look at all this, think about what direction a rock like that, a weight like that, would be trying to get something to rotate. So here's a fulcrum again. Here's our meter stick. And you have a weight over here that's going to cause it to rotate clockwise, right? If you got rid of that and instead